Hey everyone, so I just wanted to make a video going over solutions for this first handout in preparation for the first exam. All right, so I began with this graph of an updating function as well as what we can call the equilibrium line. And the first task is to identify which is which. And so the equilibrium line will always be, you can think of it as y equals x, but I'm always going to put that in quotes because it's not quite true. So there's a lot of stuff missing from this graph, and that's just because I'm taking screenshots of the graphs in Desmos and I'm not actually labeling the axes the way I can, because Desmos doesn't quite allow that. So if I'm using, for example, x sub 0 for my initial condition, then that tells me what I'm calling the variable I'm measuring in my discrete time dynamical system. What a mouthful. I'm calling them x sub t. And so this refers to a list. I have my first measurement, my measurement an hour later, my measurement 2 hours later, my measurement 3 hours later, and I'm using hours as an example. These could be minutes, days, weeks, it doesn't matter, but it's at a regular time interval. That's why it's a discrete time measurement. Okay, anyway, so this is my discrete time dynamical system, and when I have a graph of an updating function, the input axis will always be labeled with that same kind of name, x sub t in this case. It might be p sub t or d sub t or c sub t, but it's just the name of the thing you're measuring. Okay, and the output axis will be x sub t plus 1. And this t plus 1 is in the subscript, okay? All right, so that's some stuff that was missing, and so there we go, we labeled the axes. All right, let's find the equilibrium points. This also means we need to well, what is the equation for the updating function? All right, so let's find the equation for the updating function first. All right, now the blue line is the equilibrium line, the y equals x one. This red line is my updating function, and you can see that it has a y-intercept of 3. And if you kind of count and figure it out, it has a slope of 1/2. Okay, now you might want to write something like this, y equals mx plus b, but you can't. Okay, the reason you can't do that is because our input variables are called x subscript t, and our output variable is called x subscript t plus 1. So what you have to write instead is x subscript t plus 1 is equal to 1/2 x subscript t plus 3. Okay, this is the equation of our updating function. So there it is. All right, now if we want to find equilibrium, we just replace these x sub whatevers with the same variable. You can just use x. You could write x equals 1/2 x plus 3. Or what the textbook uses is x superscript star, which I think is kind of silly. I feel like they should have put that as subscript since everything else is subscript, but whatever. Okay, so let's go ahead and solve for x star. So I should move this over by subtracting 1/2 x, 1/2 x star from both sides. And that tells me 1/2 x star is equal to 3, and that tells me, so I multiply both sides by 2, I have x star is equal to 6. And yeah, we can see that whether you look at the x or the y axis, this equilibrium point here is x star equals 6. You can read it from either the x coordinate or the y coordinate. It'll always have the same x and y value because it lives on the equilibrium line. Okay, so we've done all that was asked of us so far. Now let's get to the cobwebbing. And I'm going to simplify this a little. It's a little too busy if I have you cobweb all these possibilities. So let's just cobweb with these 3 different initial conditions. So in other words, we're going to have 3 different lists. So my discrete time dynamical system is just a list of numbers. It's a list of measurements that happen at regular time intervals. And it's possible that I might have a different initial condition. So for example, if x sub 0 is equal to 2, let's see how cobwebbing works. So I identify 2, and I tell the reader this is my initial condition. This is my x sub 0. With cobwebbing, I will travel vertically to the updating function. And so I traveled this way. Then I will travel horizontally to the line y equals x, or what's really the equilibrium line. And then I just repeat that. So vertical to updating function, horizontal to y equals x. Vertical to updating function, horizontal to y equals x. And if you give yourself little arrows, you can see exactly what's happening. We're heading towards this equilibrium point here. All right, now let's make more sense of this. This point here on the one hand, I can read off its coordinates are 2, 4. On the other hand, its x value is x naught, it's the initial condition. Its y value is x1. I know this because that is what the updating function equation is trying to tell us. If you plug in x0, so you have to multiply it by half, you have to add 3, the name of the output is x sub 1. So output, input, that's what I have here. Okay, so what does this tell us? It tells us the next number on my list, x sub 1 is 4. And you could figure that out by plugging it in, but we can also read it pretty clearly on the graph. All right, now what if I want to figure out x sub 2? That doesn't happen until the next time I hit my updating function, okay? And the next time I hit my updating function, so that's this point here, my, so to speak, x value is x1, and my, so to speak, y value is x2. Okay, you should think about why that is, and as a big hint, it's because we traveled to this special line here, which is the line y equals x. And when we did that, the coordinates for this new point here are x1, x1. So you should think about why traveling here gets me the coordinates x1, x1, knowing the coordinates at this point were here. Okay, in any case, here the y value for my next point touching my updating function is x sub 2, and you can read that off at 5, or you could just plug in. If I plug in 4 to my updating function, I have 1/2 4 plus 3, and you'll get 5. This is 1/2 x1 plus 3, so it's going to be called x2. But on the other hand, I can use the numbers and I get 5. So I have x2 is 5. Okay, and you could continue this list. You would get 5.5, and then some other stuff. It gets kind of less clear after that. Okay, that's one discrete time dynamical system. But if I use other values, so now let's use x naught equals 9, or my initial condition is 9. Okay, so now I'm going to cobweb that, and I tell the reader, here's my initial condition. Right? Notice these have the same name, x naught, and that's just saying, hey, here's where I'm going to start. But what really makes the discrete time dynamical system is the entire path. It's this entire path. So let's see what path this gives us. So I travel upwards. Oh, right. Let's talk about a common error. Okay, here's what a common error is. People travel upwards, and then they go across, and they go, well, I'm not traveling towards equilibrium. Okay, the mistake is the vertical travel goes to your updating function. So when I travel vertically, I need to stop at this function. That is the function corresponding to my updating function. So vertical travel goes to the updating function. Now horizontal travel goes to the line y equals x. Vertical travel goes to the updating function. Horizontal travel to y equals x. Vertical to the updating function. And so on and so on. And now we can see, in fact, this point here is stable because I traveled towards it, whether I start on the right or on the left. And if I wanted to, I could read off some other things. So if my initial condition is 9, then my first spot, well, also, right, you could just plug 9 in here. So what would that be? 4.5 plus 3 is 7.5. But if I plug in 9, I land at this point here, which corresponds to this, and here's 7, here's 7.5. So yes, indeed, we got 7.5. Okay, so this spot here was x0, comma x1. This point here is going to be x1, comma x2. And we could read off x2. It looks like it's going to be like 6.75. That's x2. And it can go on. Okay. Anyway, I wasn't originally asking anywhere in here to write down these values, but based on how this went in class, I feel like it'll be useful for later. Okay, and then one more comment about the trick question, that is, what happens if x naught is 6? Okay, that's a terrible color. Let's do orange. If x naught is 6, okay? So this is a trick question because if here's x naught, then I travel vertically to my updating function, okay? And then I travel horizontally to the line y equals x, but that means I don't move because I'm already there. Then I travel vertically to my updating function, but again, I don't move. I'm already on it. So the point is, if where you begin, if x0 is 6, which is your equilibrium, then for all of future time, you're going to be 6. And you can see that by plugging in 6 to your updating function. You can see that by the fact that the cobweb doesn't move, right? So previously, the way I found my points for the blue discrete time dynamical system, or this path here, right, was by checking all the points where I hit my updating function and just reading off the y values one after another. Similarly, the way I found the data for my red path, I started the initial condition, I cobweb, and then I read off the y values for where I hit my updating function. This one is more subtle because I cobweb, but that's just a single point right there. And since I stay put, then for all time, I read off the y values, and for all time, it's 6. Okay, so what can this tell us about a solution function now? First off, what's a little weird, there will be a different solution function for this path, the red path. So I will call this solution function we see so many subscriptions. All right, I'll just call it S of t. There's going to be a different solution function for my blue path. I'll call this one, let's just use big X of t. This is the type of notation that I prefer. And there's a different solution function for this path, which I guess I'll call it B of t. You know what? Let's just use A, B, and C. Let's go back to that. Sorry about that. A little indecisive. Okay, so if that's B, we'll use, let's see, in red, this will be A of t. And in blue, this will be C of t. Which isn't too bad. These go in A, B, C. You can think of it like that. Okay, anyway. So, in other words, when I say I have a solution function for this data, that means if you tell me t, so like for example, if t was 3, and I plug it into my solution function, the output is x subscript 3, which in this case is 5.5. Okay. Whereas c of 3, that output would be whatever the next one is here. Oh gosh, you know what? Let's just do, we can figure this out. What is c of 3? Let's see, so if I did one more path here, so this is x2, this is going to be x2 comma x3, so I need the y value for that point, and it looks like it's about 6.25, so I'm going to run with that. So 6.25, it might be like 375 actually, 375. So in this case, I will get 6.375, and in the other case, I get 5.5. And what's a little weird is that both of these are called x sub 3, but that's because they're referring to the third data point for different paths. Okay. All right. And then similarly, if I had a b of 3, that one's nice and easy. It's just going to be 6. But this is also called x sub 3, and that's for a different path. That's my orange path versus my red path versus my blue path. And so the functions that satisfy these different things, those are the solution functions, and I have a different solution function for each path. Nonetheless, by just looking at what's going on here, we can say a lot about these solution functions. Notice, whether I'm on my red path or I'm on my blue path, I am heading towards equilibrium. Okay? Which means my solution functions, so let's talk about A of t. So A of t is referring to this list of data, and it goes on and on and on. A of t, whatever it looks like, I claim heads towards 6 as t heads towards infinity, which simply means if I continue plotting these points in cobwebbing, they are heading towards it's saying x sub t is heading towards 6 for my red path. I also know, if I look at my blue path, which had the solution function named c of t, that's also going to head towards 6 as t goes to infinity, which simply means as I move along my blue path, if I look at these y values, these are heading towards 6. Okay, so when I generated all of these different solution function curves, I had used these initial conditions that I had since erased. Okay, so more than what we're looking at now. Nonetheless, let's talk about the blue path. So what's the blue path? It's the one that begins at 9. So unfortunately, it's graphed here in red, but this is the solution function curve for my blue path. Okay, so you can ignore all of this for now. Yeah, I'll just give it all new names, so don't worry about it. So this is what I was calling C of t. It's the thing where, notice, C of 0 had better be x sub 0 for my blue path. And x sub 0 for my blue path was 9. And sure enough, right here is the point 0, 9, which says if I plug in 0 to this solution function, I will get 9. I also know that C of 1 had better be x sub 1 for my blue path. And if I go up here, that's 7.5. Let's see if it looks about right. Okay, and I know this is cut off. Here's 0. This bar here is 1. This bar here is 2, and 3, and 4, and so on. So let's see. When I plug in 1, I land right here. And yep, if this is 7, this is 7.5. So sure enough, C of 1 is 7.5. And if you continue to check, so let me give you the equation for C of t. Okay, C of t is, let's see, I think it's, I want to say 4 times 1/2 to the t plus, so no, so that better be a 3. Okay, 3, 1/2, okay. So here is my solution function. It looks very different than my updating function, which said x sub t plus 1 is equal to 1/2 x sub t plus 3. Right? This is this straight line up here from before. Okay. And notice this function here, if you actually compute c of t plus 1, well, all that means you have to do is just plug in t plus 1 for t. Okay, so I can do that. It's 3 times 1/2 to the t plus 1 plus 6. It turns out this is the same as if you were to multiply c of t by 1/2 and then add 3. So let's go ahead and do this computation. This is 1/2 times, and now I have to plug in what c of t is. So this is 3, 1/2 to the t plus 6, and then I have to add 3. Okay, this comes inside, it distributes. I have 3 times 1/2 times 1/2 to the t plus 3 plus 3. These two plus 3's become the plus 6. I have some exponential rules here, so like x to the a plus b is equal to x to the a times x to the b. So I'm using it in reverse. Here I have a 1, here I have a t. That's where the t plus 1 comes from. Anyway, all of this is to say that my solution function, normally what I would love to write is, instead of calling this function c of t, I would call it x of t, and I would say it's equal to x subscript t. And normally that would be great. I just have multiple paths here, and so it becomes ambiguous. The updating function is telling you how these y values change. So here's a change in y. And let's see, let's go to right here. This is 2, 6.75, if I remember correctly. So that's another change in y. And in fact, the change in y is, I can say more on what that is. This y value is c at 1. This y value is c at 0. So my change in y is c at 1 minus c at 0. Okay, the updating functions are telling you how these things are going to change, how these, how these steps in y change. But this is going beyond the scope of the class. So, sorry, I'm letting myself get too deep in the math weeds here. Let's back up and look at the big picture and what's happening. Let me continue to label this though. So this was c of t. It's the solution function corresponding to my blue path, which I know is a little bit frustrating because I graphed in red. Sorry about that. Okay, now the solution function corresponding to my red path, I had called that previously a of t, and it turns out, so my red path begins at 2, right? That was this value down here. So that's going to be this green curve down here, okay? So this is a of t, right? And so these solution functions, they look different because they're trying to give us different data. C of t gives me the data points 9, and then 7.5, and then 6.75, and then like 6.375, 9, 7.5, 6.75, 6.375. Whereas my red path, it began at 2, and then it went to 4, and then it went to 5, and then it went to 5.5, and then I think the next one is, oh, I should be able to figure this out. It looks like it's 6.25. That can't be right. Never mind. Sorry. 5.72. Ah, 5.75. There we go. So, right, on the solution functions, my input axis is t, and my output axis is whatever my data measurement was, my x of t. On the updating functions, my input axis was x of t, and my output axis was x of t plus 1. My updating function looks linear. My solution function, it turns out it's exponential, and it decays toward the equilibrium. And that's kind of a misuse of the word decay. In this, if I'm below equilibrium, I grow towards it, and if I'm above equilibrium, I decay towards it. But we can kind of see, like, okay, if my initial condition is up here, it's above my equilibrium value, then my path will march down towards equilibrium, and that's why we see this decrease in nature here. If my initial value is below equilibrium, then my path will march up towards equilibrium, and that's why we see this increasing nature here. Okay, so those are the big takeaways that I want to talk about, which is how, depending on how your path behaves, you can deduce a little bit about how your solution function will behave. And if your equilibrium is stable, then your solution functions will be drawn towards it, okay? And all of these are just different initial conditions. All right, so I go into more detail here, but it doesn't really matter. That's the main takeaway. Let's do this exact same thing again. So let's go ahead and do, I'll just do the one that's plotted. So here I'm beginning at 0, 3 in my solution function, which means I want my initial condition to be 3, okay, which means I start at 3, and now I'm going to cobweb, so I go vertically to my updating function, then horizontally to y equals x, then vertically to my updating function, horizontally to y equals x. I have to zoom in now to get a little bit more accurate. Vertical to updating function, horizontal to y equals x. Vertical to updating function, horizontal to y equals x. Okay, so you can see we're spiraling in towards the equilibrium. Okay, and if I were to start to get a list for these points approximately, and by these points, I really only care about the y value, but nonetheless. Okay, so what is this first y value? It's going to be called x sub 1. And it looks like it's about, so let's see, it's about 1.5. Okay, so it's about 1.5. And I only care when I intersect my updating function. Okay, this line y equals x is just to get me in the correct spot. So this is the next point I care about. And its x value is roughly 1.5. Because I basically do this swap where the old y value becomes the new x value. That's why. That is exactly why we do this move here kind of thing. Anyway, okay, and this new value is going to be x sub 2. And let's see, so that's the y value here. And okay, if like right here is about 2.3 maybe. Is that right? No, that's not right. Sorry, let's see. We have 1, 2, 3, 4, 5. So this is about 2.2. So now I'm at about 2.3 maybe, or I could just say 2.25 maybe. So I'll say 2.25. Okay, and the next time I intersect my updating function, I'm here. And Now my x value is about 2.25. My new y value is what's called x sub 3. And let's see, so this would be, wait, 2, 3, right. This is, I don't know, maybe like a 1.9 or maybe like a 1.85, something like that, for something like here. Okay, so I'll just put down it's probably like 875. That'd be my guess. Okay, so good enough. Now with my solution function, first off, in some sense, this is my solution function. And I say in some sense because if you put that in Desmos, it's not going to like it. And this is what Desmos returns. Notice it's not continuous. And that's more or less because of this issue here. What is the square root of -1? But that's getting off topic. It doesn't really matter. Even though it's not continuous, you can still get a lot of values from this. For example, I can get the value 0, 3. Okay, which means that if I plug in 0 to this function here, my output is 3, which is another way of saying that x sub 0 was 3. Also, let's see what happens if I plug in 1. Okay, I had better get whatever x sub 1 was for this path, the path that I wrote out where I began at 3. Okay, now first off, where is 1? Here's 1. Okay, 1. And notice I don't have a data point for 1, but you can kind of imagine what these two curves look like. And without saying too much, well, let's okay, what did I propose for x1? It was 1.5. Where does that live? It lives right about on this line. So 1.5 would be about there. And it looks like that would fit the data. So this point here that I added is 1, 1.5. Which is simply saying that x sub 1 is 1.5. And we can check, let's check for 2. So 2, we got 2.25. So it looks like that would be up here. Let's see, right about there. Okay, which again, it fits this weird cone thing. And so here's 2, 2.25. So now the reason we get the cone is because ultimately the equilibrium we're heading towards is 2. Okay, we can see that by looking at this point and reading off either the x or the y value. Doesn't matter. The equilibrium we're heading towards is 2, but the way we get there is by being below 2 and then above 2, and then below 2 and then above 2, and then below 2 and then above 2. So we kind of get there in an oscillating nature. And so what's happening in some sense is we have something like this. So it oscillates and it heads towards equilibrium. Okay? But we still see that now, okay, since this is a graph of a solution function, my input is t, my output is x sub t. My input is time, my output is the measurement I had on my path. Okay, so we still see that as t goes to infinity, we head towards equilibrium, which in this case, so as t goes to infinity, x sub t is heading towards 2. And so we don't have a nice decreasing or increasing nature like we had before. Up here, I just decrease towards equilibrium, and here I increase towards equilibrium. Here, it's like I'm going to increase when I'm below it, I'm going to decrease when I'm above it, but I'm going to hop back and forth a lot. And so we get this oscillating thing. So we're oscillating around equilibrium. All right. One more thing, just to really emphasize what's going on with these equilibrium ideas. And what I want you to notice is we head towards equilibrium, right? Equilibrium is 2. We're coming in towards 2, and we get kind of stuck. So we oscillate there. Here, we just come right on in some kind of decay fashion. All right. So what happens if we have more than one equilibrium? Okay. So here's an example where, all right, so here's my updating function, doesn't really matter, but if I were just cobweb with this, so I'm going to take something really close to 0. So I have 0.1, which I don't know, maybe it's here. Okay, so 0.1, this is x sub 0. And now I'm going to cobweb. So I go up to my updating function. That was kind of slanted. Let's try this again. Boom, over. up, over, up, over, up, over, up, over, I guess good enough. You know, you can see we are heading towards equilibrium here. Okay, but we're heading towards this one. We headed away from that equilibrium point because, you know, 0 is another intersection point. And if we choose something over to the right of this other equilibrium point, so maybe 8 is my x naught, okay, I have to go up. Here we go. I hit my updating function. Now I go over to my solution function, or to the line y equals x. Then I go up to my updating function, and I go over, and you can see, okay, well, now I've kind of hit equilibrium again. Okay. And if I were to choose something closer to equilibrium, you could imagine I come up, over, and we see we got a spiral nature again. And that has to do with the fact that if I zoom in a lot, this intersection has a negative slope. What do I mean? My updating function kind of has a negative slope when it intersects my equilibrium line. And that's what happened up here. My updating function had a negative slope. My equilibrium line is always y equals x. And we had oscillating behavior. So locally here, if I zoom in a bunch, if I cobweb with something close to, I think this was 6, then we'll get something like that. But that doesn't really matter. That's not what I want to talk about. What I really want to talk about is what happens when there's two equilibrium points. So then our solution function in this case, we see these two sort of, what should I call them? Sources or pinch points, attractors, I don't know what to call them. But really, if you think about it, so these are graphs of possible solution functions. Okay, you can imagine in blue, this path, I began with an initial condition of 0.1, which means 0, 0.1 had better be on the graph of my solution function. And again, that's really tiny. So you could imagine maybe it is this blue curve here. And let's see, I hope this all works out. Let's see, so whatever this value is going to be x1, and then go over. Whatever this value is x2. Did I choose that right? It's really hard to tell the difference here. No, not quite. So x2 lands here, which isn't quite as high as I want. So, all right, I was just kind of generating random curves. The actual blue curve would be somewhere in between. It would kind of come up like this and over like that, because it needs to go through the point 2, 1, which is just saying x sub 2 is equal to 1. I'm heavily rounding here, but here's my x sub 2 on that path, and you can see it's roughly equal to 1, since like right here is 1. Okay, so anyway, what I want to point out though is, since these are solution functions, my input axis is time, my output axis is the data value. And what's really going on, one of these equilibriums is stable, or it's attracting what happens as time goes to infinity. As I move this way, I'm attracted towards this equilibrium here at 6. Whereas I'm repelled from the equilibrium down here at 0. So anytime you look at solution functions, you'll see equilibriums as these things that were kind of like, if you just imagine this is a stream of water, it's what you're flowing towards. And unstable equilibriums are things where if I'm just a little bit away from 0, I'm going to flow away from it. So, okay, I just want to show you that relationship between solution functions and updating functions. I wanted to recap how to cobweb. So it's vertical travel to the updating function. Then it's horizontal travel to y equals x, which always goes in quotes. And then you repeat. Okay. And I wanted to emphasize, how do you read off? All right, so if x0 is 8, then when I intersect my updating function, which is this curve, then my input value was x0. The first y value here is x1, so I could read it off like that. In this case, x1 is 4. And the next time I intersect my updating function is all the way over here, right? This point here was not my updating function. That's just y equals x. And so it looks like x2 is 6. All right. So those are some recaps there. Let's hop to one more thing. Using all of this, okay, let's identify the equilibrium. Oh, let's first identify all my typos. Okay, so I did something kind of bad. I had labeled this axis p sub t, and I labeled this axis p sub t plus 1, and then I called my initial conditions x sub 0. That's no good, okay? I should have called these different p sub 0, because p is the name of the variable I'm measuring, and it's at time equals 0. Okay, so if I cobweb, vertical travel to updating function, horizontal to y equals x. Vertical, horizontal, vertical, horizontal. We can see I'm heading towards this equilibrium point here. All right, now if I start at this other indicated point, let's redo that one. Where are we? Use the dots. Okay, use the dots. There we go. And then over, and then down, and over, and then down, right? And vertical means up or down, and horizontal means left or right. So I go up, I go left. Oh, I go down, I go left. I go down. Okay, that's fine. So in this case, it's stable. And I have this last value here, so we come on up, we say I hit it, and you can see I'm going to go away now, and up and away. Okay, so this one is unstable, this equilibrium point here. And what might solution functions look like? Well, okay, so solution functions, my input axis is time, my output axis is p of t. Let's make up a value for this right here, maybe it's 3. Let's make up a value for this right here, maybe it's 6. So I'm trying to get these two intersection points. Okay, so maybe here's 3, and maybe here's 6. Okay, so what would happen, no matter how close I start to this equilibrium spot, so for example, these dotted lines are pretty close, or dotted line, these dots, right? So maybe my initial condition, let me zoom out a bit, maybe where I start my path is right here. Maybe this is P0. I'm still going to be drawn towards the equilibrium of 3, not the equilibrium of 6. So if my initial condition is right here, really close to 6, all right, so maybe this is 5.9 and this is 5.9. I'm going to move away from 6 and then towards 3. Okay, and that'll happen regardless, anywhere you start in this zone between the two, which corresponds to this zone, you're going to get the same kind of flow where it kind of moves away and towards 6. So these are possible curves. Similarly, if I start, let's see, okay, in this zone, so I'm below 3, then my curves, they're going to just kind of come up towards 3, like this. Boop. Right. And if I start above 6, so something like this over here, that's what we saw with this flow, then I just shoot away. So here's a 6 for reference. So maybe I start very close to 6, but a little above, and I'll just shoot up and away. Okay. So this is what solution functions might look like. And here we can see some different equilibriums, equilibrium 1 and 2. So anyway, I just want to show that relationship. What range of ICs will cause? Okay, yeah. Let's look at this question 3 really quick. So, what range of initial conditions will cause my measurements to decrease? So, I could have read this as p sub t to decrease, but those are the measurements you take. I'm imagining maybe I'm measuring population or something. I don't know. Well, you can see so initial condition, that corresponds to where I start my cobwebbing, but you can also think of it as what is p of 0 for a solution function, which means where do I start here? What's my y-intercept? And in this range here, my solution function will decrease down to equilibrium. So if I could put a star by this question, it's tricky, but if P0 is between 6 and 3, then P1 is going to be less than P0, and P2 is going to be less than P1, and so on and so on. It's going to decrease. Like we see that happening with this blue path here. I decreased, 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 Whereas if I'm to the left of 3, I increase. Okay. Anyway, that's enough for that. None of us got this far today, but just to say we should be able to do some limit practice. I think actually, you know what, let's stop the video there. We'll just emphasize all this cobwebbing solution function stuff. I think it's pretty fun. All right, see you next time.